talk more about friction, shall we? We've dealt with friction, FF, but basically I just always say the friction force is 10 newtons. The friction force is 8 newtons, right? So I'm going to sort of add on a little bit of knowledge there today. Where does friction come from? Man, I think I've even introduced you to the coefficient of friction. And as always, you write down what you think you need. I may or may not wait for it. The handout that I've just given you, these notes come from here. And in the good old days, I made kids make their own notes from this, but, well, that was a 2-day job, so. So what is friction? Force, resists motion. It involves objects that are in contact with each other. There must be contact. As a ball flies through the air, is it in contact with anything? Air molecules, right? So there is air resistance. Here's an interesting thought. You know in all the Star Wars movies when the spaceships are going from planet to planet? Like, no, I'm not trying to say that. I am saying that. Are you going today? No. Oh, wow. But like when we send rockets up and they come back from the International Space Station, they have to go through re-entry and there's all these heat shields and everything. In Star Wars, they just it's like they're parking the car in a garage kind of thing, right? No problem, that re-entry stuff they don't even bother with that. I like to stand up at movies and say that's scientifically false. I don't do that. So, what causes friction? Like, how come we have friction? Well, friction is one of those things, kind of like gravity, it's not 100% understood. Theory's still in the working stages. Object deforms a surface and vice versa, so they actually think that on a microscopic, and I'm obviously simplifying it here, right, that when you put something heavy like on a table, it actually sort of creates a little impression, if you will. A little depression, I guess, a little hole, right? And a plowing force is required to move the object over the deformation. So, in fact, I guess you could almost say that it's like going uphill, right? It's working against gravity. They believe that irregularities, objects are not perfectly smooth. And again, I'm oversimplifying things, right? And so these little rough surfaces sort of bounce over each other. They lock together. They might break off. When you're down in the wood shop and you're sanding something, you're really taking off pieces of wood, aren't you? Right? You're smoothing it out. Okay, we should talk about the difference between starting friction and kinetic friction. Starting friction is the maximum frictional force between stationary objects. So when an object has no movement, its friction is at its max. Friction is sort of a fluctuating force. It only offers as much resistance as it has to, right? Like for example, when I go to push the hole punch, right? If I just touch it, I get a little bit of friction, and I push a little bit harder, a little bit harder, a little bit harder. Friction only imposes as much as I do, and eventually friction can't do it anymore, and I have more mass than I can push it, right? But friction sort of will ramp up to a maximum. So starting friction is the maximum frictional force between stationary objects. Sliding friction is the frictional force between objects that are sliding with respect to each other. And there is a such thing as rolling friction, but rolling friction is actually fairly complicated, so we basically ignore it. We're going to. Starting friction is sometimes known as static. Kinetic friction is known as, or sliding friction is known as kinetic. Here's what we'll call some properties of friction, or characteristics of friction, or things that friction you need to keep in mind, I guess. Number one, friction acts parallel to the surfaces that are in contact and in the direction opposite to the motion of the object or to the net force tending to produce such motion, the attempted motion, i.e. it's always opposite the motion and always parallel to the surface. Right? Friction force is opposite and parallel. See that I've stopped recording. Starting or sliding friction is directly proportional to the force pressing the two surfaces together. Friction is directly proportional to the force pressing the two surfaces together. Now, if you've got a free body diagram like this, virtually all the time, right, the weight force is balanced by the normal force. The forces are balanced, right? What if you were to push down on the surface like that somehow, right? Like what if you were to, like say you're like pushing a lawnmower and you're kind of pushing down a bit. What would that do to friction? It would change. It would increase, right? Like, if I'm sliding something, if I'm trying to push my scale across the floor, and Riley steps on it, he increases it. It's a lot harder to push, isn't it, right? How come? Well, it's more massive, first of all, but there's also way more friction, right? The friction is proportional to the force pressing the two surfaces together. So if the force down is increased, then that will increase the friction. And conversely, if you do a little bit of lifting, then that will decrease the friction, right? If you're trying to slide something heavy and you can lift it a little bit, you reduce friction. And this, my friends, is called the coefficient of sliding friction. What the heck is that? The coefficient of sliding friction is the ratio of the force of sliding friction to the normal force. It is known as the coefficient of friction. It's the ratio of the force of sliding friction to the normal force. And it determines the friction force. Coefficient of sliding friction. So we need a formula for this coefficient of sliding friction, and there it is. There it is. Have you seen that funny thing before? I think I've introduced it before, right? It's called mu. And it's just a U with sort of a tail on the front. Josh Thiessen tells me, and his mother tells me, in Greek it's actually pronounced me, but every single online place I can find pronounces it as mu. I know she is, and I'm quite confused because literally everybody in the scientific community calls it mu. Apparently there's a difference between ancient Greek and modern Greek, so perhaps it was pronounced differently in ancient and it's carried on. I really have no idea. I asked her and she said it's pronounced me. But in the scientific community, we pronounce it mu. So it's a new formula for your tool bag. It's on that sheet of formulas that I gave you way back on the first day of school. Remember the Rampton flow chart? It's there. Mu equals FF over Fn, where FF is the friction force, and Fn is the normal force. So every two surfaces, if you look at this handout here that I gave you, every two surfaces will have a coefficient of friction. So at the bottom of the second page, you want to just grab that there. You see coefficient of friction table 4.1. You see that? The bottom of the second page there. So like steel on steel, 0.74. That's a high value. Sliding friction 0.57. Glass on glass 0.94. Glass on glass has high frictional coefficient. Wood on wood 0.5. Or sliding friction 0.3. Rubber road on dry tire 0.7. Rubber road on wet road. Rubber tire on wet road 0.5. Teflon on Teflon 0.04. Teflon is like that stuff you put on frying pans, that black stuff. Non-stick surface. Non-stick. Low coefficient friction. Okay, so how do we deal with this frictional coefficient stuff? We deal with it. Do you have that sample? You do. I just handed it out, right? Just handed out those sample props. I'm going to make this font a whole lot smaller because that's just way too big. Yeah, that's true. This is sad? Oh. Only 3. Won't take us long. A box with a mass of 175 kilograms pulled along a level floor with constant velocity. So some keywords there. Level floor, it's flat. Constant velocity, what does that mean? Acceleration is 0, which means that the net force is 0. The forces are balanced. If the coefficient of friction between the box and the floor is 0.34, what horizontal force is exerted in pulling the box? So here, let's draw our free body diagram. So we've got some applied force, right? What horizontal force is exerted? That's code for applied force. And we've got some friction value here that we don't know. We do know the mass is 175. How to proceed? Which one? Which one? The new one? Well, mu equals FF over Fn. We don't have FF. We don't have Fn. Can I find Fn? Because really, we've got weight force down and we've got Fn. Oh, hey, we could do this, right? We could find the force of gravity, the weight force, which is mass times gravity. So 175 times minus 9.8. $17.15? Didn't check? You can trust me. Whoops. Maybe you can't trust me. 1715 newtons, right? Negative. Which means that the normal force would be the same, only up. And now I can go mu equals FF over Fn. 0.34 is equal to the friction force over 1715. And by now you can all solve this without any problem whatsoever. How do I solve that? Multiply. That is newtons, yeah. Oh, now I didn't actually mention that. I'm gonna go back here right away. So do you get a friction force of 583.1? Okay, newtons, right? Okay, let's just pause for a second here and let's go back. I'm gonna come back to this, don't worry. Let's go back to this here. What are the units for mu? What are the units for mu? Newtons. You've been hanging around too long. Well, the units for friction force are newtons, and the units for normal force are also newtons. And newtons over newtons will cancel. No units. It is a ratio. There are no units to mu because it's newtons over newtons.
Newton squared.
No, not newton squared. Newtons over newtons.
Oh, dude.
No, that'd be newton times newtons. So if the friction force is 583.1, now technically, if you really want to get serious here, you should write F net is equal to FA plus FF. And the net force is 0. How come? Constant velocity. So then you got FA, and this is actually now, this you will not get negative 583.1 of this. You have to assign it that because it's negative, because it's to the left, right? You have to do it. It's not going to come out of your calculator. So that's going to be minus 581 583, naga. 583.1, which means that the applied force is 583.1 newtons. Do you need all this step here, do you think? I think we're big boys and girls. I think we can go to that. Right? I think we can just do this and then just say the applied force is the same, right? So really, I mean, that was a lot of yakking, but really it's only one, two, really two steps and then a statement at the end, right? So I guess maybe. Well, okay, fair enough. Probably a good idea to always draw it, right? Yeah, make it a habit. Okay, so we're trying number 2. A box with a mass of 100 kilograms is accelerated by a force of 200 newtons across a level floor. If the coefficient of friction between is 0.2, what is the overall acceleration? Oh, so this time we actually have an acceleration. Let's read it again. We got a box. The mass is 100, accelerated by a force of 200 newtons across a level floor. So we have a big FA that's equal to 200, and there is friction, but we don't know how much. What is the overall acceleration? So there is a net force, right? And this acceleration, we're solving for A. This unknown acceleration is going to come from F net is equal to ma, right? That's how we're going to get it. Jason, you appear to be just talking to someone on your phone. Do I know the F net? No. But I can find it. It's going to be the FA and the FF, right? But I need to know the FF. Weight force.
What's that point?
Lower force. 0.20 is the mu value, right? The coefficient of friction, the mu value is 0.2. You can pretty much always guarantee that step 1 is going to be Fw is equal to mg, unless they give you the weight of the box in newtons, which they do tend to do to make things simpler for you, but it really causes me grief because every kid says, what's this? I don't get this. And I have to explain to them that they've already done it for you. Sorry if that sounds like a rant. So 100 times, I guess, minus 9.8. The weight force is minus 980. Is that right? Newtons. And now I'm going to go mu equals FF over Fn. And that mu value is 0.20. We're solving for friction force, and the normal force is minus 980. How do I solve that? Multiply. Thank you. Merry Christmas, Mr. Bennett. Multiply. Now, the negative comes out of the calculator, but should it be negative?
No. You just took the force.
Yeah, but the friction force is negative, it gets to the left, right? So you're right. This, in fact, I would argue that this negative and this negative don't mean the same thing. Because this negative really means down, and this negative means to the left. So they are different sort of negatives. But it should be negative. But not because you just get a negative, right? Because it's to the left. Okay, so now what? F net is equal to? Oh, F, right, not MA. FA plus FF. We're solving for F net. The applied force was 200. Oh, minus 196. Hopefully you don't need a calculator for that. You multiply them, right? Sorry, you times them. You gazinta them. That's the net force. 4 equals 100A. How do you solve? Divide 0.04 meters per second squared.
Yay.
1, 2, 3, 4, 5.
5.
How are you feeling about these?
Why is it only
Just takes practice, right? Like everything.
to be honest, this is easier.
Yeah. Well, basically, this is the same stuff as what we did before. The only thing that I'm really adding in is this step here, right? That's all I'm really adding in. Just adding another layer to Shrek's parfait.
We add a lot of layers.
Yeah. I should get a poster up. Physics is, and the poster of physics. Picture of me, Shrek, onions, and parfaits.
Just get them out.
What do they have in common? They all have mass, yeah. Good. Okay. Does this look hard? Do you have a full page for it? Last one. A box with a mass of 46 kilograms is pulled along a level floor at a constant speed. Constant speed. What does that mean? F net is 0, acceleration is 0, forces are balanced by a rope that makes an angle of 30 degrees with the floor as shown. If the force on the rope is 260 newtons, what is the horizontal component, which we are now calling FAX? What is the normal force, and what is the coefficient of sliding friction? Do you guys have the picture?
No, we.
You don't have the picture? Okay.
This is the FA. FW equals that much.
Oh,
I don't know how you got it.
you don't know how I got this 450?
What?
You don't know? Do you know how I got that number there?
I just didn't even do this.
I didn't, for some reason, I didn't do that step, so we better do that, right? So that's going to be 46 times minus 9.8. Now let me just double check that it is, but it should be. Yep. Okay, now we have a normal force here that hasn't been drawn yet, right? And most of the time, the weight force and the normal force are equal. But, special situation, we now have this FAX, but we haven't talked, I think I just briefly mentioned it, we also have FAY, don't we? We have a component of that 260, we have part of that 260 newtons that's not only pulling sideways, but we have part of that 260 that's actually pulling up. And what is that going to do to these vertical forces? Well, it's going to cause some problems, right? It's going to cause change. It actually reduces the normal force. Whoops, wrong one. Why does it reduce the normal force? Go away. Well, because this guy and this guy have to add up to which one? To that one, right? All of the verticals have to balance out. So if I'm applying an upwards FAY, then that reduces my normal force. The table doesn't have to push up as much. And because the table doesn't have to push up as much, that's actually going to make the FF smaller. And I think this makes sense, right? Like if you're pulling on something heavy with a rope like this kind of, right? And you want to lift it up and make it easier, you kind of do what? You increase the angle, right? If you just pull straight sideways, it's going to be sitting heavy, right? What are you laughing at? If you lift up a bit, it's going to reduce that friction. Okay, so now I guess we got to find the horizontal component, and we're going to have to find the vertical component, aren't we? Fortunately, you all paid close attention in grade 9 math when you got introduced to trig. Right? So here we have FA, here we have FAX, here we have FAY, the Y or vertical component. This is 30 degrees, I think, and this is equal to 260. Okay, so the FAX is adjacent, which means we're going to use which one of the trig functions? Cos. So FAX is equal to, do you remember, did I give you this formula already?
Yeah.
I think I did, right? Did I not say FA cos theta? Right? So 260 times cosine 30 225.2. That's sideways. And so the accompanying step, FAY, is going to be FA sine theta, exactly. How come? Because FAY is opposite. Sine is opposite over hypotenuse. FA sine 30 130 newtons up. Can you feel yourself getting smarter? Okay, now, what do I do with this new FAY? Again, it's reducing that normal force, right? I think you get it. The problem is always, how do we write it out? So here's sort of the latest way that I've been trying to get it through people's heads. I'm going to write F net Y, the net force in the Y direction, and we know it's going to be equal to 0, right? The F net Y is 0 because this object is not accelerating up or down, it's just sitting there. Even if it's moving sideways, the F net Y is 0, right? And what makes up this F net Y? Well, we have FW down, we have normal force up, and we have FAY. These are all the three forces that are acting vertically on the object, vertically. And the sum of them is 0, because it's not moving. Okay, so now let's fill in the blanks. What do we know? We know 0. Our FW is now. Is the sign important here? How come? Because some are down and some are up, right? So the sign is super important here. So this is going to be minus 450.8. I don't know the normal force. And the FAY is 130, and that is in the upwards direction, right? So I want my Fn to be positive, so I'm just going to leave it there. And I'm going to take the 450 to the other side, and it's going to become positive, 450.8. I'm going to take the 130 to the other side, it's going to become negative. So really, you just take the weight force and you subtract the FAY. That's what we're saying. So the normal force is 320.8 newtons.
So what do we need to do to say why do we?
Ooh, that's a lot of work just to there.
That was B. Yeah.
Yes.
So.
This is A. I guess technically this is the start of B, right?
Yeah.
And this is the end of B, because B said normal force, right? Okay, so that means we're almost done, I guess. So I guess we're starting at C now. C asks for the coefficient of sliding friction, which is mu equals FF over Fn. I don't know. I know Fn. I don't know FF. I don't know FF. No, we're asking for the coefficient of sliding friction. Mu equals FF over Fn. I know Fn. I don't know FF. What is FF equal to? Let's look back at our free body diagram. FF is opposite FAX, and we know right at the start I made you do this. Constant speed, what does that mean? It means those are equal. And really, I would suggest you write this down. Really, all along I've been saying this. F net, I just haven't said it. F net x, the net force horizontally, is 0, constant speed. And what's that made up of? FAX and FF. That's really what I've been saying all along. I've just simplified it by saying they're equal to each other. Right? And so now I'm introducing this sort of notation because you kind of need it to make this one make sense. So really, I mean, and I'm okay with you just saying FAX, FAX was 225.2, right? So therefore, the friction force, FF, is minus 225.2. Right? But that's really what's going on. And the last step, mu equals FF over Fn, right? And we're solving for mu, aren't we, right? So my FF is 225.2. My Fn is 320.8. I'm going to answer that question right away. 0.70. Oh, what's going on? Okay, yes, the question is it negative? And the answer is no. Because this is a ratio, we don't care about direction. Mu is not a vector. Mu is actually a vector divided by a vector, which is not a vector, which is kind of weird. But yeah, we don't worry about direction, so we don't need any positive or negatives in there. If you did it, I'm not going to worry about it now, but eventually you'll realize it's not a big deal. Emily? Okay, yeah. Yeah, at this point, I get it. You're still kind of learning it. I'm not going to get too excited about it. But generally, they're just stated as a number. But the one thing you should know is this. Generally, mu values are less than 1. Okay, they are almost always between 0 and 1. If there's a mu value that's bigger than 1, that's really rough. That's like bus duty for a whole week when it's minus 40 out. That's rough. I think if I'm not mistaken, there are some problems on this handout. Yes, I'm right. Okay. So there are some sort of starter questions here that you can work on. There's not many. There's a code, but there's no link. I'll try it for you. I know, awesome. Yeah, I know. I will post solutions as well. I've got another set here for you as well, because practice, right? Okay. Sure.
What's a horizontal horse? Is that
And A is horizontal. All right. Get in, I suppose. Try. That's what I mean.
I will,
Okay, so you got a little over 15 minutes to get this done.